last time, remember, we did the Bolzano-Weierstrass theorem, right? Can anybody remind us what the Bolzano-Weierstrass theorem says?
From the notes?
No, not looking at your notes.
Oh, okay.
See if you can remember it, right? What is the Bolzano-Weierstrass theorem about, roughly speaking?
About neighborhoods, what we just did.
Neighborhoods, okay.
Punctured neighborhoods.
Punctured neighborhoods. Okay, yes? You're getting closer.
Points.
Accumulation points, getting better, getting closer. Right, warmer, warmer. Right, accumulation points. Something, 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 something. Always has an accumulation point, right? Yep, right? Are we gonna say that?
Tonic sequences, at least that one.
You started off good, but no. So bounded is in there. Bounded, you have a set, it's bounded, and there are infinitely many elements in the set, right? Then you're guaranteed to have an accumulation point. Okay, so that was the Bolzano-Weierstrass theorem. So, okay, so today we're going to talk about Cauchy sequences. This is a really important idea. It is related to what is usually called completeness. Okay. So earlier in the text, you have this thing that they call the completeness axiom. I think it's more accurate to call that thing that we had earlier the least upper bound axiom. Okay. The least upper bound axiom is going to give us what we normally call completeness. Okay, and we'll talk about completeness today. So completeness, you can't really talk about completeness until you have this notion of Cauchy sequences. Completeness is a statement about Cauchy sequences. Okay, so let's start off with the definition. So you have a sequence. You have, okay, and it has this following property. So if for every epsilon, there exists an n such that if n and m are bigger than n, then the distance from an to am is smaller than epsilon. Then we say that a sub n is a Cauchy sequence, after the great French mathematician Cauchy. Okay, so you notice that this is kind of different from what our definitions were earlier, right? What kind of the notions that we had earlier, right? You see that we're talking about 2 points. We're not talking about a single point being close to some number. We're talking about two points being close to each other. Okay, so what we're saying is that after you can find if somebody gives you a small distance, there's some point past which everybody is within that distance of each other, right? They're all within that distance of each other. Okay, so it's talking about right. So you've got these guys, and they're getting closer and closer and closer to each other, right? They're getting closer and closer and closer to each other, right? Which seems to be sort of like saying that they're converging to a limit, right? But it turns out it's not exactly the same thing. Okay, so another way of talking about this is, so you have your sequence, right? You have your sequence, right? And you look at well, let's see it this way. Okay, so here's A1, A2, A3, A4, 5, A6, A7, A9, 10. Right. Okay. So if we consider consider all elements past a certain value. Okay. Consider all elements past a certain value. Okay. And this you consider to be like the tail of your sequence. Right? You're throwing off the head elements, right? And you're left with the tail elements. Okay. And so what this is saying is that you can make the diameter of the tail as small as you want. Right? Like the distance between elements in the tail, you can make as small as you want. Yeah.
So I'm a little confused about the construction of this sequence, because the way you drew it is kind of like this almost random order of how it goes. It's not like this rotating spiral. What are the exact? Could you go over again exactly how the construction of the sequence is?
I'm just making up some sequence. This is not any particular sequence.
Okay, so it could be
it's just
any type of two-dimensional sequence.
Yeah.
Okay, as long as
But these guys are getting. I'm trying to draw a Cauchy with what I'm imagining as a Cauchy sequence. Maybe this is not helpful.
okay. The key point to take away from that diagram, though, is that the distance between each point is shrinking.
That's right. The distance between pairs of points. The distance between pairs of points is getting closer and closer to each other.
Okay.
Okay. But anyway, let me just not. This is clearly not working. So let's do some theory that will actually make it give you some real intuition about what Cauchy means. Okay. So let's start off with this following simple observation: that if a sequence converges, then it's Cauchy. Okay, so you have actually a lot of examples of Cauchy sequences. Anything that you've seen before that is convergent is a Cauchy sequence. Okay. Okay. So why is that reasonable? Cauchy means that given any distance, you can find a time past which pairs of guys are close to each other. Right? Hold on one second. Right? Convergent means that given any distance, you can make everybody within that distance of a particular point. Right? There's a particular limit, and you can make everybody close to that. Right? So, well, if they're close to that, then they must be close to each other. Right? So, if you can make everybody close to L, then certainly you're making everybody close to each other. Right? So it's that intuition that, of course, convergence implies Cauchiness. Okay, yeah, Mitchell.
Does Cauchiness imply convergence?
So, we'll get to that in a second. And the answer is no. The answer is no. Not always. Okay. Yes?
Can you have Cauchy? My logic is so flawed. I don't know if this is the same thing Mitchell asked, but can you have a sequence that does not converge that is still Cauchy?
Yes. It's the same question.
This is okay.
Yeah.
So bad.
That's okay. No, it's okay. Yeah.
Also, just to get the definition of a Cauchy sequence, you could have a situation where the points are getting further and further away from each other, but then at some point hit some sort of like tipping point, and then it starts converging together. And
Sure. You don't care about what happens at the beginning.
It's not about the head; it's just the tail.
Exactly.
Okay.
Yeah. Any sort of limit statement. Well, yes, exactly.
I'm kind of confused about like the pair of the ends.
So we're saying that. So let me draw a picture that maybe actually is helpful. Okay, so you have your sequence. Suppose you have a convergent sequence. Okay, so they converge to L, say. Okay, so these guys actually converge to L, right? Can I say, is this sequence Cauchy? Right, to be Cauchy means that if I give you some distance, there's a time past which everybody is within this distance of each other, right? So if I say, this is a magic time, that would mean that this guy and this guy, whoever he is, must be within this distance of each other. Any pair, n and m, any pair of guys whose indices are bigger than n must be close to each other, right? This guy and this guy, whoever, right? This guy and that guy, they all must satisfy that to be Cauchy. Okay. Okay. Yeah. So, right, such that if these are bigger than n, then they're close to each other, right? So whenever these guys are bigger than that. Okay. So the proof, I guess, is pretty clear, right? You say, well, look, we want to show that given epsilon, they exist in n, such that if n and m are bigger than n, then the distance from a sub n to a sub m is less than epsilon. And you say, well, since a sub n converges to some value L, say, we can make them close to L, right? And if they're close to L, then they're close to each other by the triangle inequality. Right? So you say, since these guys converge, they exist in n such that n bigger than n implies that the distance of a sub n to L is smaller than epsilon over 2. Right? But then, if you have two guys past then, we see that the distance between them equals a sub n minus L plus L minus a sub m, which is smaller than, by the triangle inequality, a sub n minus L plus L minus a sub m, which is smaller than epsilon over 2 plus epsilon over 2, which is epsilon. Right? So the proof is this: if you want everybody to be within epsilon of each other, well, just notice that because they converge to L, you can make everybody within epsilon over 2 of L. But if they're within epsilon of, if there's a time past which everybody is within epsilon over 2 of L, past that time, all pairs must be within epsilon of each other, right? Because they lie within this world that is, whose length is L. Epsilon, excuse me. Yeah, Mitchell.
So do Cauchy sequences need to be bounded?
Yes. Yes, they do. Yeah, I forgot. That was actually something I wanted to say before this. That observe Cauchy sequences are bounded. Thank you, Mitchell. It's like, I forgot to say it. Cauchy sequences are bounded, right?
Because then there's the maximum epsilon, right?
Well, you could just take an epsilon of 1. So you have a Cauchy sequence, let epsilon be 1. That means that past some time, everybody is within one distance 1 of each other, right? So you fix, right? So here's my sequence. Okay, so past some time, like suppose here's after this point in time, say, suppose it goes like this: 1, 2, 3, da 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 da, a sub n. And then everybody's up here, say. You know that everybody is within 1 of each other, so you just choose one of them, let's call him A and naught. Everybody's within one of A and naught, right? So they're bounded. And of course, these guys are bounded because there's finitely many of them, right? So yeah, it's certainly true that Cauchiness implies boundedness. Yeah, so that's easy. Maybe I'll have you do it as an exercise. Just for practice of writing. Okay. Okay, but is everybody okay with this argument here about the? Any questions about that? Yeah, Mr. Markham.
We can always say that L minus AM is the same as AM minus L, right?
Yeah.
Okay.
Yeah. Because you multiply by -1, which is absolute value 1. Right? L minus AM in absolute value is the same thing as, right? If you have A minus B, that's the same thing as -1 B minus A. Right? But that's absolute value. Remember that the absolute value has this nice property that the absolute value of a product is the product of the absolute values, right? So this just becomes 1. It's the same thing. Yeah,
I think one thing that I'm a little confused about
Yes.
is when we first started, it was like every single possible step we wanted to show and so on. And then over time, as we've been learning more things, we're kind of like, we can kind of assume that we know certain steps and don't have to like.
Well,
Yeah,
I mean,
okay.
if you write it out, so I mean, I'm not giving you the whole proof. I'm not writing out the whole proof here, but I'm just giving you the idea.
If we were writing that out for like an exercise or, or an exam or whatever,
Yeah.
would you still want us to take that extra step and flip it and say that it's equal to
Oh, this
AM?
thing here.
You know what I'm saying?
Yeah.
Where,
No.
because like
that's-
first exam, you definitely would have wanted us to do that because that was kind of where we were.
That's right.
So,
That's
like,
right. That's right. But you know,
We should just generally get a gauge of like, if we've done this 50 times, we can.
yeah,
just-
basically, yeah.
Okay.
Yeah, it's true. I mean, because we were talking about the absolute value at that time,
Exactly.
right? But you know, we already talked about the absolute
Okay.
value. Kind of, yeah.
Or like the triangle inequality property. Like,
Right. I mean, you would need to cite the triangle inequality
okay,
here.
we still need to.
Yeah. I mean, probably should cite the triangle inequality.
Okay.
Yeah. Okay, let's go on. So in answer to Mitchell's question, right, so we've just seen that every convergent sequence is Cauchy, and what about the converse, right? Does every Cauchy sequence converge? And the answer is no. One example is to consider, suppose we are in the rational numbers. Okay, suppose we are in the rational numbers, and you have the sequence 1, 1.4, 1.41, 1.414, 1.4142, which is the beginning, just take the decimal expansion of the square root of 2 and take further and farther down the sequence. Okay. This is a Cauchy sequence, right? This sequence is Cauchy, right? Because you see that you differ by smaller and smaller, right? These, if you look at the difference between these guys, right, it's on the order of thousandths, right? If this guy differs from everybody else, but on the order of thousandths, right? These guys, if you start from this guy and compare it with anybody, it's on the order of 10 thousandths, and so on and so forth, right? So this sequence is Cauchy, but there is no L such that the sequence converges to L. Right? There's a hole in your space, right? There is no square root of 2 in the rational numbers, right? So there's nothing that you converge to. Okay. Although in R, it's funny, right? In R, the sequence does converge. right? So you have the sequence that, you see that Cauchiness actually depends on the space that you're in, right? It's not, I'm sorry, the convergence depends on the sequence that you're in, right? Okay. Okay. I don't think we'll be able to get through the proof of the next thing, but let's start it. Okay. So here, theorem, and this is usually called R is complete. Okay. So maybe I should introduce the terminology. Like we call well, I can see why I didn't want to introduce the terminology. We call a space complete if Cauchy sequences converge. Right? If all Cauchy sequences converge. Okay.
In metric space, did we define this previously?
Yeah, we haven't defined metric space. That's probably why I don't have this definition in my notes. So yeah. Anyway, we call R complete because all Cauchy sequences converge in it. You don't have to know what a metric space is. Just know that. Right? In Q, you could have Cauchy sequences and they don't converge. In R, it turns out that all Cauchy sequences converge, and so we call it complete.
Are R and Q examples of metric spaces?
Yes.
Okay.
Yeah. Metric basically just means a distance. So metric space is just a space with a distance. Now, what's a distance? We have to define that. So this is actually one of your possible final project topics, and a good one if you guys want to switch.
What is a good topic?
What's a good topic? Metric spaces.
Oh, the metric spaces.
Yeah. Actually, a very good topic. Okay. Okay. So the theorem is in R, a sequence converges if and only if it's Cauchy. Okay. Sequences are convergent if and only if it's convergent if and only if it's Cauchy. Okay. So one of these sides we just did, right? We already saw that if it converges, it's Cauchy. Now we need to show the reverse direction, that if it's Cauchy in R, then it converges. Okay. So suppose that A sub n is Cauchy. We want to show, what's our goal? Our goal is to show that there is a point that is the limit, right? We want to find an L, right? We want to show that there exists some L in R such that A sub n converges to L, right? In other words, for all epsilon greater than 0, there exists an n such that n bigger than n implies A sub n minus L is less than epsilon. We want to find this L. We want to find the L. Okay. We have a sequence. We have a Cauchy sequence. Right? So it's bounded. We have some Cauchy sequence in R. Right? We want to find an L. So what we do is we consider the set S of all values of the A sub n. Okay. This is not the same thing as the sequence, right? This is just a set of values we look at the values of this as a set, right? For example, if your a sub n is -1 is -1 to the n, say, right? Then there's infinite guys in your sequence, but there's only two values, right? -1 and +1. Okay, so in this case, your S would be just -1 and +1. Okay, that's not a good example because it's not Cauchy, but you know what I mean. Okay. So, okay, so there's two possibilities. S is finite or S is infinite. Okay. Okay. Case S is finite. Suppose S is finite, right? Then there's only a finite number of values, right? So say that S is a finite set of values.
A sub n sub p.
Yeah. So, right, like here in our A1 was -1, A2 was 1, A3 was -1, A4 was 1, and so on and so forth, right? I could choose two of these guys, and they are all the values. So A1 and A2, those are all the values. Okay, so here I'm saying that suppose there are p values. Suppose your sequence takes on only p distinct values. Okay, at some indices. Okay. Claim then A sub n must be constant after some point. Okay. So this actually is your homework. So, okay, let's stop there. We'll talk about the infinite case next time, which relies on the Bolzano-Weierstrass theorem, which relies on the least upper bound axiom.